Okay, welcome to Unit 10. This is the last unit, and it's going to be chapters 28, 29, 30, and a little bit of 31. And so it's all about magnetism, magnetic fields, and the way that magnetism relates to electricity. So we're going to be looking at circuits, we're going to be looking at forces on charged particles, and all kinds of things like that. So, things you already know about magnetism. There's a north and a south pole. In reality, we've only found things that have north and south together. If you cut a magnet in half, you don't get just north and just south, then it redistributes north-south. That would be a monopole. If you had something that was just north, it would be a monopole. And those are theoretically possible in things like string theory, but they haven't been discovered in reality yet. Opposite poles repel, or opposite poles attract like poles repel. And so that should bring up an interesting question. If you hold up a magnet, in the Earth's magnetic field, what direction will the north side point? It'll point to what we call magnetic north, but then that's actually south, right? The Earth's south pole is what we call the North Pole, because that's the pole that attracts the north side of a magnet, right? So keep that in mind. And so magnetic fields, it's a field vector. It points, and it goes around the magnet, and they look, the field lines look like electric field lines. We're not going to get into drawing them as much as we did with electric fields, because we're not going to get into like the number of charged particles and stuff like that. And we measure the magnetic field in Teslas, which is a totally new unit if you haven't studied magnetism. I thought it was kind of funny. I was going for my MRI at one point, and it says, caution, 3 Tesla magnet. And I'm looking at that thing to myself, oh yeah, people are going to look at that and be like, oh, 3 Tesla, I need to be careful around this thing. Permanent magnets have a permanent magnetic field. Electromagnets can be magnetized if you run an electric current across them. The North Pole is the end from which the field lines emerge. The South Pole is the place where the field lines go to. Monopoles, we talked about. Crossed fields, that's where you have an electric field and a magnetic field perpendicular to each other. Like, for example, light. Light is an electromagnetic wave. The electric field and the magnetic fields are perpendicular to each other. Okay, other important things. Right, field lines work the same as they have before. The density of the field lines tells you the magnitude of the field. However, differences between electric and magnetic fields. The force on a charged particle does not depend on the field lines there alone. It also depends on the velocity. There's only a force on a charged particle from a magnetic field if the particle is moving. And we'll see that in the equation, right? F equals QV cross B. Well, it's coming up. And so, an electric field produces a force on a charged particle whether it's moving or not. So that's a difference. Also, the direction, the electric field produces a force on the charged particle in the direction of the field line, right? Tangent to the field line. The magnetic field produces a force on the particle perpendicular to the velocity of the particle. And so since it's producing a force perpendicular to the direction of the velocity, the magnetic field technically does no work, right? Because work is a dot product. Perpendicular vectors give you a magnitude of 0. So our main unit that we're going to use is a Tesla. And a Tesla is 1 Newton per amp meter. So 1 Tesla is 1 NAM, N over AM. You can see that a Weber is a joule per area, so it's how much energy there is through a certain area, or rather joules per amps. So it's how much energy there is per amount of current, and that's over area. A Weber we'll talk about later, and it's Weber, not Weber. A Weber. And 1 Gauss is 1/10,000th of a Tesla. So sometimes it's good to use Gauss instead of Tesla, like the Earth's magnetic field is half a Gauss. So it's a smaller number, but it doesn't make a huge difference. Tesla is the main thing we're gonna do here because we can express that in terms of the other SI units, newtons, amps, and meters. So the first equation we have is F equals QV cross B. So it's a cross product. And don't forget the order here matters. When you're figuring out the direction of the force, you put your fingers first in the direction of the velocity, and then you cross in the direction of the magnetic field. And then the direction your thumb is pointing, that's the direction of the force on that particle, right? And the magnitude can be calculated as QVB sine theta. And so in the first, in those pictures there, you can see there's a magnetic field pointing to the right, and then the velocity is either to the right or to the left. There the force is 0 because the movement, the velocity, is parallel to the magnetic field. However, in the other one, the magnetic field is pointing to the right, and the velocity is pointing kind of forwards a little bit, right? And so again, you point your finger in the direction of V, and then cross in the direction of B, and the force ends up going up, right? That's that right-hand rule. And then for the other one, same thing, right? It's moving, if you're kind of holding the paper flat like this, the particle is moving towards you, the magnetic field's going to the right, so again that produces an upward force. Okay, and so then question is, at what angle between V and B is the magnetic force a maximum? Hopefully by now you know cross products 90 degrees is going to give us the greatest magnitude when dealing with a cross product. And so, example 1, indicate the direction of the magnitude and direction of the magnetic force in each situation. So for A, B and V are parallel to each other, so 0. There's no force. B, by the way, when we're dealing with a negative charge, we just reverse direction. So if the V is to the right here, we just reverse direction and point our fingers in the opposite direction of the negative charge's velocity. But here also they're anti-parallel. The angle between them is 0 or 180 degrees, and sine of 0 and 180 is 0. In C, here the velocity is sort of to the right of the page, and the field is down a little bit, 60 degrees, and so the force is into the page. So you would draw a circle with an X on it, right, to show the back of the arrow that's going into the page. For D, velocity is to the right, magnetic field is up or away from you, so the force is coming out of the page. Right, so you would draw a circle with a dot. E, V is going towards the top of the page, B goes into the page, and so the force is to the left. For F, the velocity is that way, but we reverse direction because it's a negative charge, right? and it's coming out of the page, so V is going to the bottom of the page, B is coming out of the page, so F is to the left. And then for G, V is kind of going to the bottom of the page to the right, B is going to the top of the page and up a little bit, so F is coming out of the page. For H, V is going this way, B is into the page, so the force is perpendicular to the velocity vector in the plane of the page, right? So 30 degrees above that dotted line that's drawn there. And B, or I, in I, V is into the page, sorry, out of the page, and the magnetic field is that way, except that it's got a negative there. So I think the V and the B are supposed to be switched. So imagine that those are switched, that the velocity is towards the top of the page, but we reverse direction because it's negative. But then that would actually make it the same as I, or F. So let's imagine that the negative should be drawn in the one that has the V next to it. So the velocity is out of the page, but it's a negative, so we point into the page. B is towards the top of the page, so the force would be to the right, if the negative sign was in the circle next with the V next to it. Okay, so let's do a numerical example here. We're going to do V cross B here. And so I write I, J, K, that's a messy one. I and j. Again, you may have learned other ways to do this, but as a reminder, this is the way that I showed you. You don't have to do it this way, but so here it is. And so I go down through I this way, so it's negative 6 times negative 5, so it's 30 minus, and then going up this way, 0, so it's 30 I plus, and then for j, I go down this way, so it's 4 times 3, 12, minus, and then to go j this way, I go that way, so it's minus but plus 10, j, plus, and then for k, I go down this way, so that's 0, minus negative 18, so that's 18k. All right, so that's the v cross b, and then what I'm going to do now is, so let me simplify this, 30i plus 22j plus 18k. So now if it's a proton, what I do is I take this and I multiply it by q, because the force is qv cross b. So this is v cross b. So then for part A, it would simply be the charge of a proton. So I take 1.6 times 10 to the negative 19th, and I multiply it by this. And so what I think that ends up being is the force vector is 4.8 times 10 to the negative 18th I plus 3.52 times 10 to the negative 18th j plus 2.88 times 10 to the negative 18th k. So that's the force on a proton. If this thing is an electron, then it's just, so this is the force on a proton. The force on an electron is just negative times the force on a proton. And since this is a negative, you just put negatives in front of each of these, and that reverses the direction, goes in the opposite direction. Now, one place where we have moving charges is when we have current. So if I have current in a wire, and that wire is in a magnetic field, and that can actually produce a force on the wire. And if I look at the units QV, I end up with coulombs, meters per second, right? So if I switch the seconds and I get coulombs per second, now I've got current. And then multiply that by meters, so that's like current times length. So force is also equal to IL cross B. And so that's our next equation here. And you can see in next to example 3, this instance where we've got a magnetic field coming out of the page and this wire. If the current is going up in the wire, so IL, so the current is going up, magnetic field is out of the page, that produces a force to the, in this case, looking at the page, to the right, and so that pulls the wire to the right. If the current is going down, right, so down, and then B is out of the page, that produces a force to the left if you're looking at the page. So for A, question A, example 3, the whole thing there, the magnetic field is going into the page now. And so if this current is to the right, so I, L cross B, B is into the page, that produces an upward force on A, right? Whoops, here we go. Can you see that? For B, now this one's going this way, so B, the current's going that way, the current is into the page, so that produces a force, or the magnetic field's into the page, that produces a force downward. For C, the current is down, the magnetic field is into the page, so we curl into the page, that produces a force to the right. And for D, it's coming down, and the magnetic field is into the page, that produces a force perpendicular to the wire. Okay, so pointing at a 90-degree angle down away from the wire to the right. Okay, so let's take a look at example 4. Okay, one challenge in this question is reading it and understanding it. Right, so you've got a current carrying a wire of 100 amps due west, and it's suspended between two towers that are 50 meters apart. The lines of force of the Earth's magnetic field are uniform there and enter the ground in a northerly direction at an angle of 40 degrees with the horizontal. Okay, so this is a three vector kind of problem. So here's the current. This thing is 100 amps, and this wire is 50 meters long. This is going due west. All right, and now this is coming down into the ground at an angle of 40 degrees. So so now this is west. So if I turn this kind of sideways like that, and I have the current going away from me. So now here's this wire. The magnetic field is coming down this way. And if this is north and this is south, right? Because if you have this, as they say, never eat soggy waffles. And so if north is this way, that means west is that way and south is that way, right? And then coming out of the page is east. But this is what's happening here. And this angle is 40 degrees. Okay, and so IL cross B is going to be 100 amps, that's I. L is negative 50 meters I. Okay, so I'm treating east and west as my x-axis, all right? And so that means that north and south is going to be my, let's see, yeah, north and south is going to be my y-axis, and up is going to be positive on the z-axis. Okay, so how is this pointing now? B is going to be 5 times 10 to the negative fifth times cosine of 40 j, right? Because that's this component of this thing. That's the j. Minus 5 times 10 to the negative fifth sine of 40 k. That's going to be this, kind of going down. Okay. Okay. And so now, you know, when I do this, what I end up with is this cross product. So this is 100 out front. Let me erase this, create a little more space. So 100 times, so this is 50, 50, this is 3.8 times 10 to the negative fifth, negative 3.2 times 10 to the negative fifth, etc. And so now when I do my cross product, what we end up with is that the force is negative 0.16 J minus 0.19 K newtons. And so if we find the, what are we looking for here? So if we find the, all right, we multiply these using the Pythagorean theorem and do inverse tangent. All right, notice this is in J and K. There's no east-west here. So the force on this thing is just in the up and down, right? So a little bit down, and then also a little bit south, right? And so this is going to be 0.25 newtons with an angle of negative 130 degrees. So that's if we're looking at this from the side, right? Like this. North is over here, here's up, down. So it should be pointing down a little bit, kind of that way, right? Because it's negative J and negative K. All right, so for number 5, we're looking to support this thing in this magnetic field. And so we want the force to be equal to the force of gravity. So F equals IL cross B, but across the sine of 90, which is the perpendicular, so it's just ILB. And so I've got 0.01 kilograms, kilograms per meter, rather, times 10, because it's Yeah, grams per meter. Now the grams per meter, right, this is the force of gravity, would be this times 10. And this meter part, that's this, that's the L, right? So it's like force per meter equals I cross B, but the B here is 2 times 10 to the negative 10th Teslas. So this is I times B. And so if I take this, which ends up being 0.1, and divide that by 2 times 10 to the negative 2, I end up with 5 amps is what the current has to be. All right. And so now this works with, even if we have to split up a wire into like a lot of little pieces. So we take, and we add up the whole path, the total force on the wire is still IL cross B, even as we're adding up all those little places where L is the straight line path from one to the other. Because if you're adding up all those little pieces, things that are at different angles will eventually cancel each other out. You think of it that way. And so even this wire that's in this next example, right, there the force on the wire is 0. Even though, one side's a little longer and then there's that curved part, all of that is eventually going to cancel out somehow when you add up all the components in the different directions. So the force on any loop, if the full loop is in the magnetic field and it's constant size and constant current, then the force is going to be 0. And then in example 6, let me draw this one. And so A says find the magnetic force on the straight section of the wire. Well, the straight section of the wire, the force F is IL cross B, but L here, this length is 2 times the radius, and I is, this vector of the length is perpendicular to B, so this is just going to be 2 IRB. All right, and then what direction is this going to be if we're looking at this as a vector? Right. Well, current is this way, magnetic field is up, so this is into the board, so it's going to be negative 2 IRB in the K direction. And what about for the top half of the arc, right? That, when you add up all these pieces, right, there is some up component here, but then that gets canceled out by all the down components over here. And so here the current overall from here to here is that way. So IL, right, IL, L is ultimately that way. IL cross B, and this is coming out of the page, right? So F is 2 IRB. Okay, and so then the total force, F net, on the whole thing is 0 newtons. These should all be newtons, by the way. And so then what about D? Well, the force here on this part is into the page, right? And the force on here is out of the page, so it's going to spin like this, where this part of it is going to be coming out of the page, and then this piece is going to be going into the page, and so it'll spin top forward. That'll end up being the resulting motion. And then if I have circulating charged particles, so what happens is, because of the way these magnetic fields work, I can send a charged particle into a magnetic field, and it's going to end up going in a circle, right? And so, QVB sine theta, QV cross B, that's what we end up with as the force. And so if we have something that's ending up going in a circle, right, in a magnetic field, then the force is a centripetal force. So we have another type of centripetal force, so that ends up being QVB equals mv squared over r. And when we solve, if theta is 90 degrees, right, then we end up with QVB equals mv squared over r. And so that ends up being r equals mv over qb. The way that I remember this, I don't know why, but it just sticks in my head. I tried to come up with something, and I come up with read my very quotable blog. I don't have a blog, and if I did, I don't think it would be very quotable, but that somehow is in my head. Read my very quotable blog. So it helps me remember that equation. And that's important because we're going to be seeing a lot of this type of thing where we've got particles going into a field and then it turning, and so we're analyzing what happens to the radius of the curvature as it's going in. And so in example 7, we want to know the paths of these various charged particles of equal mass when they enter the uniform field. So equal mass is important because equal force on equal mass is going to produce an equal acceleration. And so those are going to produce, if the charge is the same, also, because that's important in this equation, different radii for the particles here. And so the first one, that would be this one, this positive particle coming in. The positive particle is moving this way, right? And this is coming, the magnetic field is out of the page. That's going to produce a vector down, right? And so it's going to end up having, it's going to curve back down around underneath, right? This one is a negative charge. So you reverse the direction of the velocity, and then B is coming out of the page, so that's a force upward. So that's going to produce that type of motion, right? And then this one, this is a negative charge, so again we reverse. Here the field's going into the page, so it's like this way into the page, it produces a force downward. For this next one, notice it's two negatives. So I am doubling the charge. If I double the charge, that means I cut the radius in half. So whatever you made as the radius of this path, cut that in half, and that'll give you the radius for this one as well. Okay, and you can count that just in terms of these kind of like grid lines almost. Okay, and then in example 8, all you're doing is you're taking that read my very quotable blog equation, and you're substituting in, you know, if you have 2q, then that cuts the radius in half. And you're saying if this is going to be clockwise or counterclockwise based on the information, right? It's the same uniform field directed into the paper. And so you're imagining this particle coming in kind of like this one, right? It's coming in, but it's, since it's into the paper, positive q would be that way into the paper, so it would produce up. That would be a counterclockwise, sorry, like this one, right? B is into the paper, V is going that way in, up, so that would produce a counterclockwise radius going that way for this first one. Positive 2q, same direction counterclockwise, except that now the radius is cut in half. Now negative 2q, so this is going to produce the opposite direction, like this one, right? But it's 2q and 3m. The m is on top, q is on the bottom, so it's going to end up being 3 halves. 3 halves are clockwise. Ooh, see that? And then this next one, 2q, 2m. So those cancel out, but there is still the v. So it's twice the radius, but it's positive, so it'll have a counterclockwise path. This one is negative q, but 3v, so it's 3r, right? The v is up top, so if you multiply 3 times v, then you have to have 3 times the radius, 3r, and it's negative, so it'll be clockwise, just like this one, right? In a magnetic field going into the page. And then here, negative 3, 4, and 2. The q is on the bottom. The 4 and the m and the v are both on top. So you end up with 8/3 r. 8/3 r, and this one's clockwise because it's negative, just like this one. So going down the radii are r, half r, 3 halves r, 2r, 3r, and 8/3 r. And then all the positives are counterclockwise, all the negatives are clockwise. And what can also happen then is we end up with these circulating charged particles, where it's given just a little bit, like these are circles, so these are coming in and they are perpendicular, the velocity is perpendicular, but if the velocity is also directed into the page a little bit, that piece that's parallel to the magnetic field, there's no force on that, so it's not going to accelerate. And what you end up with is these helical paths. These are not spirals. Spirals, by the way, spirals is where the radius gets smaller, right, so it gets closer in. Something going at a constant radius but moving along like that is a helix. And so that's why for the gene they say DNA, it's a double helix. Spiral staircases are mostly actually helix staircases. So anyway, you can end up with this type of path. And then also you can see that you can have magnetic bottles. Right? So by manipulating the magnetic field, if you have charged particles in there, you can hold those charged particles in place without ever having to touch them, just by creating and manipulating the magnetic field. And that's really useful for things where they're doing nuclear experiments and they have very, very, very hot substances. So hot that if you put them against any other substance, they would melt them. But you can hold them in place away from other things by producing a magnetic field. And so that's it for our introduction to magnetism.